Okay, so linear approximation is really just a fancy word for, or taking the linear approximation or the linearization. That's really just a fancy way to say that we're going to use the tangent line to approximate the value of the function, because we don't really want to work with the function itself because the function might be kind of ugly, particularly for the type of value that we're putting in for that function. So for linear approximation near the point of tangency, the tangent line can provide a good approximation of the true value of the function. However, the tangent line can only provide an approximation, not an exact value. The only place where the function itself and the tangent line will have the exact value as each other, the same value as each other, is going to be at specifically the point of tangency. So the thing that you have to remember is, let's say I'm trying to approximate a function value at 8.2. I might be writing the equation of the tangent line at x equals 8. So at x equals 8, the tangent line and the function value are the same, okay? But at 8.2, that's the number we're going to be putting into the tangent line after we've written it in order to come up with an approximation for the function value at 8.2. So you are going to have to juggle two x values, one that you're going to write the tangent line with, which is the spot where it's the point of tangency. The other one is where we've moved away from that point of tangency a little bit to get an approximation. That number is usually like some kind of decimal number that we have to deal with. If the decimal number gets the decimals bad enough, it'll show up in a calculator section. But a lot of times it's just like, a tenth or 2/10, and it's something we can still easily multiply out. So those will end up being in the non-calculator section. Okay. All right, so the linear approximation equation, this is its official formula. If you look at an equation that says, like, what's the linear approximation, we'll note that f of a is approximately equal to L of a. L just stands for the linearization equation. But you also are allowed to just write the equation of the tangent line. Now notice this doesn't quite look exactly like the equation of the tangent line, but it is. Okay, it's just written in function notation. So what is f prime of a? What does that stand for? Slope, right? F prime is going to be the slope where at x equals a, right? So this is just our slope. Let me get a pen to write with here. This piece is just our slope at x equals a. A is the value of a at the point of tangency. And then what would f of a be? That's the y value at x equals a. So for a minute, if we go back and let's say we had some ordered pair of 1, 4 and a slope at that point of 2, does everyone agree that we would get y minus 4 equals 2 times x minus 1? Agreed? Okay. Well, what if I just isolated the y here by keeping this 2 times x minus 1 exactly as it is and just adding the 4 on to the other side so that it says y equals instead of y minus 4 equals. Everyone buy that? Now look at that compared to the linearization equation formula. Isn't that what it is? Okay, slope, the x value where we did the point of tangency, and the y value of where we did the point of tangency. Okay, so it really just is the tangent line rewritten so that its y is isolated. That's all it really is. It just uses function notation because usually we're trying to find out an approximation for some function. And so it uses function notation instead of the xy notation, but it really is the same thing. You're not learning to write a new type of equation at all. Okay. All right. So we just talked about that. Okay. So if the function is concave up at the point of tangency, then the approximation will be an underestimate. This is of course something, this is going to be like a TTK you'd have to memorize, right? If the function is concave up at the point of tangency, then the linear approximation is what? An underestimate or an overestimate? Well, you really can just visualize this. Okay, so if you have concave up, you just want to visualize, okay, let me think about something that, is looking like this. If I were to draw a tangent line to it, where would the tangent line be? It would be under it, so what you're getting from the tangent line is too small. Okay, so what happens if the function is then concave down at the point of tangency? then it's an overestimate, because if I were to graph that, then I graph the tangent line on something that's concave down, we will notice that that tangent line is going to be above the curve. Everywhere except for the point of tangency, that's going to be above the curve. And because of that, that makes the value we're getting from the tangent line bigger than the value we're getting from the function itself. Okay, so good? All right, so let's do a couple. Example number 1, given that f of x equals 2x squared plus x minus 3, find the linear approximation or the linearization of f of x at a equals 2. Okay, so really that's just a fancy way for us to say, hey, write me the equation of the tangent line at x equals 2. So what would we need to write the equation of the tangent line? We always need two things, point and slope, right? So let's find the point. We have the x value is 2. How are we going to find the y value? Substitute, okay? So f of 2 is going to be 2 squared, which is 4 times 2, which is 8, plus 2 minus 3, so 7. So our point of tangency at x equals 2 is 2, 7. And then the slope is found how? Derivative. So we're going to take f prime of x equals 4x plus 1. We're going to evaluate that at x equals 2. So we get 8 plus 1, which is 9. Okay, so the equation of the tangent line then, y minus 7 equals 9 times x minus 2. So that's the equation of the tangent line. Technically, they asked us for the linear approximation. So it's really the only difference between writing the equation of the tangent line and the linear approximation. You go one step further and add the 7 over. So 9 times x minus 2 plus 7. So there's our linear approximation equation. Notice it doesn't ask us to use it yet, just to write it. Good so far? And technically you could distribute this whole thing out, but you will find that these problems are far easier if you don't, because usually then what happens when you put in a number, because that number is going to be sort of close to 2, when you subtract them, you usually just get something like a tenth or 2/10, and that makes the math easier than if you're going to distribute it all out. Okay, so I would not distribute that all out. Okay, so now it says use the linearization to approximate f of 1.9. Well, now that's just as simple as saying that f of 1.9 is approximately equal to whatever we get when we put 1.9 into the tangent line equation. So that's what it means to use the tangent line to approximate that, is we're literally just going to substitute that number into the tangent line instead of substituting it back into f of x. Substituting 1.9 into f of x is going to give us the exact value of the function at 1.9. This is asking us to use the tangent line to just approximate what that number is. Okay, so first we're going to subtract 1.9 minus 2, which gives us negative 0.1. Well, negative 0.1, when you multiply by 0.1, what does that do? Just moves the decimal, right? So we get negative 0.9 plus 7. Okay, so what's negative 0.9 plus 7? 6.1. So the tangent line approximates the y value at that point to be 6.1. Notice we are using the approximately equal to sign in this because we know that that function value isn't exactly equal to 6.1, but it is approximated by the tangent line itself. All right, so that is a basic example. What do you think of that? Not too bad? Okay. All right, so we're going to do a multiple choice question. Okay. So a differentiable function f has the property that f of 5 equals 3 and f prime of 5 equals 4. What is the estimate for f of 4.8 using the local linear approximation at x equals 5? Okay, so this is really just asking us to do the same thing, but it asks us all in one big step. Notice it asks us for the local linear approximation at x equals 5. That's just a fancy way of saying write the tangent line at x equals 5 and then use it to approximate at a value of x equals 4.8. Okay, so first let's start with the tangent line itself. So in order to find the tangent line at x equals 5, I need a point. Do I have that? Yes? Okay, and I need the slope at x equals 5. Got that too. Okay, both of those things are given. So if we write the equation of the tangent line, we get y minus 3 equals 4 times x minus 5. So the linearization equation is just that same thing with the 3 added over to the other side. So there's a linearization equation. And we want to use it to approximate an x value of 4.8. So now we're just going to substitute in 4.8. And this is a non-calculator question. Okay, so we take 4 times negative 0.2 plus 3. Well, 4 times negative 0.2 is negative 0.8. So this is going to be 2.2, or A. All right, how's that? Good? Good. Okay. All righty. Last example, but a bigger example, okay, with more subparts to it. Let f be the graph such that f of 1 equals 4 and the slope of the tangent line at any point is given by dy dx equals 3x squared plus 1 over 2y. So now you're starting to see that we can also blend these into implicit type problems. How would we have gotten, they don't tell us what the function is, but they do tell us its derivative is 3x squared plus 1 over 2y. And since the derivative itself contains both an x and a y, that tells us probably we had to do an implicit differentiation to get there. So that's going to tie us into that first part of this unit. Okay, find the equation of the tangent line to the curve at x equals 1. Well, in order to find the equation of the tangent line, I need two things. I need a point. Well, do I know what the value of the function is at x equals 1? Yes, they give that to me, 1, 4. But what about the slope at x equals 1? The slope comes from finding dy dx. Now, in this case, dy dx is a function of both x and y, so we're going to need to substitute both of those things in at the same time. So dy dx evaluated at 1, 4 means we're going to put 1 in place of x and 4 in place of y simultaneously. So we're going to get 3 times 1 squared plus 1 on the top and 2 times 4 on the bottom. So that gives us 4 over 8, or a half, when you reduce it. Okay, so now we just have to actually write the line. So y minus 4 equals 1/2 times x minus 1. So notice this question's a little different. It doesn't ask us for the linearization. It just asks us to write the equation of the tangent line. So as far as we know from what we've seen in the problem so far, this is just like a basic old question we've already answered somewhere else in the course. But then in part B, we get into the fact that we're going to use that to approximate, because now it just says use the tangent line to approximate f of 1.2. So now we're just going to make sure that we move the 4 over. So f of 1.2 is going to approximately be equal to 1/2 times 1.2 minus 1. And I'm going to add the 4 on over to the other side to make it the linearization, the linear approximation equation. Now, here's where things get a little bit interesting with your no calculator and you haven't been doing kind of some of your more basic arithmetic calculations in a while off of a calculator, is what do I have going on when I've got a fraction and a decimal combined? Okay, well, you can either convert the fraction to a decimal and work the whole thing in decimals, or you can convert the decimal into a fraction and work in fractions. Okay, I'm going to work in fractions. I do better in fractions, believe it or not. So I'm going to work in fractions. This one actually comes out a little bit nicer in fractions, at least to me. So what happens when you take 1.2 and you subtract 1? What do you get? 0.2, but 0.2 is 2/10, right? So if I make that 2/10, then my 2's are going to cancel out. And that's just going to give me 1/10. Well, 1/10 as a decimal is 0.1, okay? So my approximation is 4.1. I find it easier to work in the fractions because oftentimes you can turn that into something over 10 or something over 100 And that makes that pretty quick to do some quick, reductions out. You can even then put your answer in fractions if your answer makes more sense in fractions, because it ended up just being 1/10 that I was adding to 4. It made more sense just to convert it back into a decimal. If it was a little bit crazier of a fraction that it ended up being, we might want to just keep that whole thing in fractions. Okay. All right, so that's part B. So that's pretty much what our lesson is today, right? But there's still 2 more subparts. So then the question is, where does this really sometimes go from here besides just using that equation to plug a number in? What else could we do? Okay, so now we're going to say determine the second derivative at the point 1,4. Now the second derivative at the point 1,4 is going to require us to do a quotient rule. And remember that this is implicit because we're taking the second derivative with respect to x, but there is a y in the problem. Okay, so this is going to go back to the first half of our unit and tie kind of all of that together. So the second derivative with respect to x is going to be low, which is just 2y, d high, which is just 6x, minus high, so 3x squared plus 1, d low. Now what's d low? 2 dy dx, not just 2. Okay, all over 2y whole thing squared. Now, I could do some cleaning up of this. I could substitute in that entire giant fraction of 3x squared plus 1 over 2y for dy dx, but I'm not going to do any of that because in this case, the goal is not to get to a nice simplified version of the second derivative, it's to evaluate it. So it's better to go ahead and start evaluating it just as it is and start putting the numbers in. So now we're going to evaluate this at 1,4. Okay, so every time we see y, we're going to put in a 4, and every time we see an x, we're going to put in a 1. So when I put a 4 into this first y right here, 2 times 4 gives us 8. When we put a 1 in for this first x, 6 times 1 gives us 6, minus 1 squared is 1 times 3 is 3 plus 1 is 4. And now's where the fun comes in. What do we put in for dy dx? 1/2. Okay. How do we know we put in 1/2? We calculated that in part A. dy dx at the point 1,4 was calculated in part A when we wrote the equation of the tangent line, and we've already determined that dy dx at the point 1,4 is 1/2. Okay, so this becomes 2 times 1/2 all over 2 times 4, which is 8, so over 8 squared. So now we just have to clean this up a little bit. 8 times 6 is 48. Okay, this 2 times 1/2 is just going to simplify down to 1. So 48 minus 4 over 64. Okay, or 44 over 64. Those are both divisible by 4, so 11 over 16 is the reduced answer. You can leave it as 44 over 64, though. So there's a little review of implicit differentiation. Okay. And then in part D, is the approximation in part B an underestimate or overestimate? So there's something that from this lesson that we have not actually seen an example of yet. That's why partly why this example is in here. How do you determine if what you're getting from using the tangent line to approximate the function is too high or too low? You have to know the function's concavity at the point of tangency. So the point of tangency here is 1,4. Do we know whether this function is concave up or concave down at the point 1,4? Yes. Okay. Why? Because we know the second derivative is positive. Okay, we just calculated it. It's a positive number. That means that at that point, at the point of tangency, the function is concave up. Okay, so imagine the function's concave up. Where would the tangent line be placed compared to the function? If the function's concave up, it would be below it. So the approximation we're getting in part B is an underestimate. Okay, so we would say the approximation in part B is an underestimate because the second derivative evaluated at 1, 4 is positive, therefore concave up. And that is it. That's our lesson.